Hey y'all, let's talk about spanning trees. So there's a few things that you need to know about a spanning tree before, well, here we go. So spanning trees have a few important properties. They do not have circuits within them, so there will be no circuits. They are connected graphs. They have to be connected. And then they follow an important one-off, that's what Dietz has been calling it, kind of ratio between the vertices and edges. So this is, I think this was your homework on March 9th maybe, and it asks you, question number 2 asks you which of the following graphs is a tree. So you need to look at each graph and decide, is my graph a spanning tree or not. So if we look at, let me change my color. Let's try that. If we look at number 1, there's a few different ways that you could look at it and kind of start to calculate whether it's a spanning tree or not. Some of them you'll be able to certainly look at and tell just from looking at it whether it's a spanning tree. For instance, if I look at graph number 3, this very clearly has a circuit within it, right? So if you were to label each of the vertices, whatever you wanted to label them, I gave them these letters, I could clearly say that A, B, C, F, A is a circuit, right? So, graph 3 is not a spanning tree because it has a circuit in it. It is a connected graph, so that would be, one step towards becoming a spanning tree, but it is not one. But graphs like 1 are going to be more complicated or just require a little bit more work to figure out whether or not they are spanning trees. So certainly you could ask yourself for graph number 1, is it connected? Yes, it is. Graph number 1 is connected, right? There's not 2 parts of the graph that we're looking at. But does it have a circuit? Some of you could probably look at it and say, no, I don't see a circuit there, but others might be a little confused and not sure if you can see one or not. So what I would suggest doing is counting the number of vertices and edges. So if I look here, you've got, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 vertices in this graph. And then let's count the number of edges that we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we have 11 edges. So you'll notice this is the one-off ratio, right? You have one more vertice than you have edge. So if you wanted to write a spanning tree kind of formula, you could say that vertices are equal to edges plus 1, or vice versa, you could say that edges are equal to vertices minus 1. So this is a connected graph. It does follow the one-off ratio, and so yes, this graph is a spanning tree. Oops, sorry. Let's look at graph number 2. If it did have a line right here across the bottom on our Christmas tree looking spanning tree, then certainly it would not be a spanning tree because it would have a circuit within it. But it's open, so I don't see a circuit straight off, and it is a connected graph. Sorry, I got a new pen. It's just not working great. And I would if you want to be certain, you could count the number of edges and vertices. So like you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 edges here. Edges, it's an E. And then let's count the number of vertices. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So, and you have 15 vertices. Ooh. Vertices. There we go. Hopefully you can read that. So you'll see again here that your edges are equal to your vertices minus 1. So if you think about it, here in graph number 1, you had one more vertice than you had edge, and here in graph number 2, you have one more vertice than you have edge. So yes, this is a spanning tree. It is a connected graph. It does not have a circuit, and it does follow the one-off edge to vertice ratio. So the second part of the question is asking you, calculate the redundancy for each of the graphs. So let's understand what redundancy is. Redundancy. Ooh, I know that looks awful. The pen's not cooperating. So redundancy has to do with how many possible edges need to be removed in order to make a graph a spanning tree. So for redundancy, you'll need to know a formula, and that is, sorry, I had a technical issue and needed to erase what I had written because it looks so bad. So redundancy, y'all are just going to have to bear with my awful handwriting on this thing, is equal to edges minus vertices. I'm going to put an E for edge and a V for vertices plus 1 in most cases. So redundancy is going to tell you how many lines you need to get rid of, or how many edges you need to remove to make a graph a tree. So if we are calculating the redundancy, we are calculating the redundancy most often, or what we'll be doing in our class at least, of a graph that is not a tree. So if you look at graph number 3, right, we already discovered, or can look at it and tell that it has circuits in it. So you need to figure out how many edges do we need to remove to make this graph a spanning tree. So you would do that by counting the number of vertices and the number of edges to start, and then using the redundancy formulas. So we could look kind of and easily tell that there are 6 vertices, right? So I'm going to put V is equal to 6. Okay. Edges might be a little more complicated if you aren't familiar with it, so I'll just count them with you. You've got 1 edge, 2, 3, 4, 5, 6, 7, 8, 9. So I won't write it in yellow. For edges, you've got 9 edges. So you'll see we obviously know that graph number 3 is not a spanning tree because it does not follow our one-off ratio. If we want to calculate the redundancy for graph number 3, you would just say 9 minus 6 plus 1. Okay. So 9 minus 6 gives you 3 plus 1, right, equals 4. So we need to remove 4 edges from this graph in order to make it a spanning tree. That's how you calculate your redundancy. If you get a redundancy that is equal to 0, that means that your graph is already a spanning tree. Oh my goodness. A spanning tree. Hopefully that's helpful. Let me know if you have any questions about redundancy or figuring out if your graph is a spanning tree.